See, so we are trying to make people understand what is gravity, right? For that, first we need to know. See, by around 400, 500 years ago, people realized how the solar system looked like through careful thinking, observation, and all these things. They came to conclusion that sun along the planets go around the sun. So then, around 1620s, I think, a great scientist called Newton, he was sitting in his garden and he saw an apple fall down, right? Rather than just ignoring it, he asked a wonderful question, and that is, why the ball fell down, not went up? That looked like a simple question, but that's what scientists do. Then he realized, okay, Earth attracts something called, eventually it was named as gravity. So Earth has kind of attraction force. Then he imagined an experiment. If you take a ball and throw it, obviously it goes in an arc and falls down. Throw it a bit faster, even farther in an arc. Even faster, even farther, right? So the ball is trying to fly away, but ultimately Earth is attracting. So then he realized something amazing, Newton. So we are talking about Newton's gravity here, the classic gravity, old gravity. So he imagined a cannonball experiment, as you can see, right? Imagine a cannonball shooting. With certain speed, it falls down. The higher speed, it even goes farther and ultimately falls down. And even faster, even farther. So then he realized the ball is trying to fly away. It has certain speed, but ultimately it is getting surrendered to the Earth's gravity. Then Newton realized if we have a high enough speed, then it goes and comes back to the same and hits you back in the head. So that's one of the craziest ideas, very clever thoughts in the history of humanity, because that means this is an ever falling ball, as it is trying to go away, but it is again falling towards the Earth. And in this case, the ball is neither flying away nor falling towards the Earth, nor hitting the Earth. So it is forever falling object, which he called as gravity, and the speed was calculated as 7.8 meters per second. So if you do that, 7.8 meters per second, then you can put anything into the orbit around the Earth. That's changed humanity technology forever. So he realized the orbit, and still scientists use those calculations to send orbits, to send the satellites into the space. So Earth had attraction force, like we have seen this, right? Yeah, yeah, like this. So you have a little animation here.
Newton envisioned the firing of a cannonball with increasingly greater explosive thrust. He reasoned that with enough velocity, the bounds of gravity could be broken, and the cannonball could escape to orbit.
So it is forever falling object, a satellite is, right? So that's why the moon orbits the Earth. The moon is trying to go away, but ultimately falling towards the Earth's gravity side. So it's a perfect balance between outward gravity and the outward velocity, speed, and inward gravity. That's what an orbit is. That's how the satellites are put around the Earth. If you have ever seen a satellite, it goes and it tries in that it changes its direction to go around the Earth. That's a real satellite. That's a real rocket launch. That's how it looks if you see. So then what happens is it changes its direction and it goes towards around the arc of the Earth, try to attain that speed, which is 7.8 kilometers per second, and depends upon how altitude, different heights, different speeds, basically, right? So and ultimately it is put down around, put in an orbit around the Earth, right? So that is one thing. So that's why you can see the satellites, they forever fall towards the Earth, forever falling objects. So this is called Newton's gravity. Right? This is the Newton's gravity, forever falling objects. So now, this is the first part. I want the 7th graders to do this part, because I'll try to pause. So this is Newton's gravity, but Newton didn't understand that force or whatever, how this gravity pulls across empty space. He was himself confused. Yes, you are trying to fly away, but ultimately Earth is attracting. But how Earth is attracting along empty space? What is that mysterious force, that how it acts along crowds and crores of kilometers. He was really mysterious. So he said, no, I don't understand gravity, right? Then the next guy comes in after 200 years later. The question was still unsolved, right? So he imagined an experiment simply. If gravity is a force, Newton said it has a force, then you must be able to feel it all the time. But that's not the case, right? For example, imagine a man falling off of a roof somewhere from a tall building. So while he is falling, he feels weightless, which is exactly how he feels if you go to very far from the planets or stars in a space. That's how you exactly feel, completely weightless. If gravity is a force, it must be acting on you all the time. But here that's not the case. Then what is gravity? Right? So then he extended this experiment. He did an amazing elevator thought experiment. Right? Imagine you're on a 200 or 300 floor building, on top of the building, inside an elevator, you are just standing with a coffee cup. Right? And if the elevator's cables are suddenly cut, then the lift starts falling, the elevator starts falling, and as long as it's falling, while falling, before it hits the ground, all the time you will be feeling weightless. If you leave your cup, it will be before you and the thing will be falling. Exactly, everything is weightless, right? Which is exactly how you feel if this elevator is far from the planets and stars in an empty space. Like how you feel the elevator lift is falling, that's how you exactly feel if you are in an empty space somewhere. And if you are in a closed elevator, you won't be able to tell the difference whether you are on in a free fall on the earth or weightless in the space somewhere. You will not be able to tell the difference, right? So then gravity may not be a force, it is simply maybe something related to motion itself. He thought. So then the same way, so falling under gravity, floating in the space, he realized is the same. Einstein. Then, which is why, right? Right? Which is why, because astronauts, if you see the spacecraft, astronauts sitting inside the spacecraft, and we've just discussed orbits, that spacecraft is going around the earth always in the free fall. Because they are falling, they are feeling weightless. Otherwise they are still under the influence of gravity, but they are freely falling, they feel weightlessness, not because they are far in the space. You understand? That's a realization here. Because astronauts feel weightless because they are continuously free fall around the earth, not because the gravity is not there. That's a wonderful thought. Now Einstein went further and he imagined this. So, freely falling under gravity, if you are in a closed elevator, you think you will be in the space, and exactly the same feeling when you are actually in the space. If you are in a closed elevator, you will not be able to tell the difference. Both the time you may think that you are in the space. Right? Now, same, he extended his experiment. This is wonderful, this thing. Let us say you are inside an elevator. You are standing on a weighing machine inside the elevator, let us say. Obviously, you will be standing like this, and all the things are pulling you, and it is compressing the drinks, whatever, on the weighing machine, and it is showing you some reading. That's your weight. It depends upon how Earth pulls you, how strong the object pulls you. If you are in a Jupiter, if you are saying you have 50 kg here, on Jupiter, I think 2.5 times more gravity, so it pulls you more. The weighing machine shows you around 250, 50 into 2.5, like maybe around 200, something like that. It will show you. So on Jupiter, you will weigh more because it attracts you more with a higher gravity. So yeah, your Earth is pulling you. But if you are in this elevator, imagine this is in a very far from the stars and planets where there is no gravity, and you have rockets attached to it. And if you start the rocket starts obviously accelerating the entire elevator upwards. And Einstein realized at a certain speed, 9.8 meters per second, which is Earth's gravity. If you do that, if the rocket is accelerating upwards, you will be forced against the floor, against the weighing machine. At certain speed, at certain acceleration, you will feel exactly like the Earth. You can walk, you can do, if you are in a closed elevator, you will not be, if you are big enough elevator, you will not be able to tell the difference whether you are on the gravity on the Earth or or accelerating in the space. So Einstein realized, man, good, this is so gravity and acceleration are same. It cannot be differentiated, right? That's the craziest idea. So this is called Einstein's equivalence principle. What is that called? Einstein's equivalence principle. Now, so gravity is not a force. That's what. Then gravity may be related to, is the shape of the environment maybe you are moving through. Einstein thought, if it's not a force, then why do planets go around the sun? Maybe it's the shape of the space itself. He thought it's not a force. If it's a force, you must be feeling all the time. Then it may be the shape of the space time itself, right? So right? So, if gravity is not a force, then what is it? Einstein realized. Because on the earth we are standing and accelerating in space in a elevator, both are the same. If gravity is not a force, then what is it? Why do planets go around? Maybe it's the shape of the space itself, he thought. So, which leads to his thought, the space-time fabric, right? So the space-time fabric. So this is Einstein thought, heavy object space is like, the space-time fabric. You take the entire space, it's like a fabric, and heavy objects bend the space-time, creating a curvature, and the other planets simply follow the curvature, right? As you can see here, right? So this is a space-time fabric. You can put a heavy ball and it bends the space-time fabric, right? And other things, if you take a smaller ball, lighter ball and do it, it keeps orbiting, right? That's what Einstein, because it is the shape of the space itself, Einstein thought. If it's not a force, it must be the shape. That's the only solution he came up with. That's space-time fabric. Now, so heavy objects do not pull on the other objects because there is some invisible force, but they bend the space-time. They bend the space-time. And the planets don't move in circles because the sun is pulling them with a rope. They move in a way because the surface itself is curved and the planets simply follow the curvature. Right? That's the idea. The space-time curvature. And the matter, all this is made up of matter, right? So matter tells the space-time how to curve, and space-time tells the matter how to move. Right? That's the idea. Now, that's a very reason why moon is following the earth in an orbit and the sun and all the planets go around. So the heavier the object, the deeper the bend, which is actually, in terms in astrophysics, it's also called gravity well. What is that called? Gravity well. Space-time fabric, or under it you can say gravity well, because it's creating a gravity well basically, right? Now, as the massive objects, so the heavier the object, the deeper the bend, the deeper the gravity well. The sun, we have certain bend. A neutron star is very dense, and I'll give you the calculations around, we discussed, I think somewhere around 10 to 20 kilometers. So if you take the entire sun, and it will be only 10 to 20 kilometers, if after all the thing is left, right, then you will be left with only 10 to 20 kilometers radius. Take a 13 lakh diameter sun, and 13 lakh diameter sun, if it's become 10 to 20 kilometers diameter, just the size of Mount Everest, that's how dense, small is a neutron star, and the density will be very high. Even if you take a spoonful of the material matter, it will up to 4 to 5 trillion tons, because a lot of gravity is concentrated in a very small place. Now you go further, because this happens when big stars die, right? If a star is around 10 to 20 times bigger than the sun, right, after the end of its life cycle, it keeps even collapsing even smaller than this, and around 2 to 5 kilometers diameter, which becomes a black hole, right? So that's the heavier objects. Now that's a black hole. So as you can see, the black hole, right? So as you can see, only 2 kilometers, I think. If a star is 10 to 20 times bigger than the sun, right, at the end of its life, it keeps collapsing until it becomes very small, only 2 kilometers in diameter. That becomes a black hole, extreme gravity, where light even cannot escape, along which it forms a boundary called event horizon. Now, event horizon, right? So the last station would be ours, would be time dilation, right? Time dilation. As you can see, right? The gravity bends space-time, Newton realized, and heavier the object, heavier the bend, deeper the well. So deep that even light cannot, so heavy, the gravity is so extreme that light even cannot escape, right? And one thing amazing that this was found was actually near heavy gravity, time slows down, right? Time slows down. The clock ticks. This was tested by scientists as well. Our next station would be something like this, like as some of you have trying to plan something we discussed. That's up to you how you creative you want to be. So if you have two clocks, and Raghavendra has already told you two different ticking clocks, right? At different rates, ticking at different rates. If you have two watches, come up with a solution. On top of a mountain, let us say you can take two characters from you as well. So one would be holding at the ground level, sea level, and the other would be at the mountain. Two clocks, if you put, right, they both tick differently. Scientists have found it. Of course, this is in milliseconds. It's really hard for us to calculate, but this is milliseconds. Stopwatch or anything, Sir has given some ideas, like maybe use a capacitor or weaker batteries, maybe you can use. So the time ticks down, time ticks slow near the strong, because you're closer to the gravity, you're farther from gravity. As you go farther, time moves faster and faster. As you come near the gravity, heavy gravity, this was proven already. Now if you take the different objects in the space, different objects have different like the gravity is different, the gravity wells, right? Now if you take the black hole, the gravity slows down dramatically. Like let us take two friends experiment, like anyone, two characters. What's your name? Sharanya. Sharanya. Oh boy, we need a boy. Sharanya. Shresht, we already done this experiment. And yourself? You both are okay. Lakshanya and Shresht and Sharanya. Let us do. Sharanya, he is here. Yeah, Sharanya, he is wearing a watch, and Shresht there, he goes in a spaceship near a black hole, right? Goes for 1 hour according to his watch. So he goes for 1 hour and comes back. And right now both would be around how old are you now? 13. You? Let us say you imagine you are also 13, right? Yeah. Let us say you both are 13 years old, and Shresht goes in a spaceship near a black hole, travels near a black hole for 1 hour according to his watch, and when he comes back, Shiranya says, "I've been waiting you for 10 years." How come? Because his watch ticked slow near the black hole. Not because his heart beats slow. Everything is normal for him. Everything is normal. That's the craziest part of space-time, right? Everything is normal. He breathes normally. His heart beats normally. Everything is normal. But it is just that, when you compare the watches, when you look at the life aging and everything, simply, it's unbelievable. He didn't age it. He aged very slowly. That's the reality of the space-time this thing, right? That's a two-friend experience. This was actually brilliantly shown in the Interstellar movie. So that's our time dilation. And the next station would be nice printout, something like this. I'll give you some this thing. The color printouts we need, right? The colored ones we'll do, right? So in the Interstellar movie, basically they run out of resources on the Earth. Earth is not habitable anymore. They need to find a new planet. And astronomers find that there is a planet near a black hole called Miller's planet, right? Gargantuan is the name of the black hole. They go near to find a planet which has water, because it must be habitable. So they go in a spaceship. They travel near a black hole for a few days, they find this planet, right? And when they come back, actually, her daughter, who was 10 years old, now she became very old, and he'll still be the same. He didn't age much at all. So this is the reality of the space time dilation. Heavy gravity slows things down. And at the near the black hole, when you enter the event horizon, at the edge of the black hole, time literally stops. Time stops. Right? So that's the idea about the gravity, how gravity controls the time. Right? So that's a bit about